Okay, here we go. These are some formulas that revolve around logarithms. I did 1 day of trigonometric review with you, and this is your one chance to see logarithms and exponential functions. Okay. So we start at the basic situation here. It says express the following equations in exponential form. If you want to understand a logarithm, you have to understand exponentials. What does log base 2 of 8 equals 3 mean? Yeah, and so, you know, sometimes people think about like a loop-de-loop. I don't know, the 2 picks up the 3, goes to the 8. I don't really know. I just think that this is always the exponent. That's what I think, and I think that this is the base. So 5 to the 4th is 625. 6 to the negative 2 is equal to 1 over 36. Why is it negative 2?
Because it makes it go down.
Makes it in the denominator. Very good. And this last one would be what? Be the x is equal to a. Very good. So you've seen it written in exponential form. Now let's take these and write these in logarithmic form. Log base of equals 2. Here we have log base 18 of 1 equals 0. Okay. Log base, don't have to write the base of 10. Base 10 is assumed. You can write it. 1 over 10,000 is equal to negative 4. And here, log base m of p is equal to n. Good. So logarithms are useful because they solve for exponents. Logarithms are used often in the physical sciences, such as physics and chemistry and others. Anybody here think about a chem major? Wow. Man. Make a lot of money. Nobody here likes money. Engineer. Who's going to be an engineer? All right, we got one.
You can make a lot of money.
Yeah, YouTubers, they make great money.
They actually do.
Yep, they great. Yeah, you do it. Log base 3 of 9 is equal to x. Solve for x. What is x? Why is it 2?
3 squared equals 9.
Yep, because 3 squared is 9, so x is 2. We have natural log. What is the base of a natural log? The base is e, so this is really log base e of what? Of 1 is equal to x. That's what that means. So if you were to write in exponential form, it means e to the x is equal to, what power do you take something to get 1? 0. So x is 0. Okay? We're going to skip this one because it's written incorrectly. Go ahead and try D, E, and F on your own. D, E, and F on your own. Go. Well, x equals 3. Okay, letter D, you should get 1/16. Any questions there? Letter E, you should get 3, and letter F, you should get 3. Any questions how I did letter F? No. Nobody?
Yeah, how did you get that?
So I looked at this situation, and what I did is instead of writing x to the negative third, I wrote x to the positive third, and that means that you just take the reciprocal. So x to the third is 27. These statements are equivalent. If that doesn't convince you, x to the negative third is 1 over x cubed. So does that convince you that those two, if this statement is true, then this statement has to be true? Yeah. Now what number do you cube to get 27? 3. So x is 3. E to what power is, e to the 0 power is? Here's one that's a little bit more challenging for you. 8 to what power is 4? No? How about this? As you try to think through this, if I don't know how many people are still going to be taking the ACT or retaking it, but this would be a common question for the ACT. So you got 8 to the x power is equal to 4. 8 and 4 can both be written as a base of 2. So notice that this is 2 to the third power times x is equal to 2 to the second power. See how I wrote them with common bases? Yeah. So now you just have a basic equation. 3x is equal to 2, so therefore x is 2/3. Okay, so the part that you're going to be using tomorrow as we take derivatives is expressed in problem number 4. So this is the most important thing for you to focus on today. It says use the laws of logarithms and exponents to write the expressions with no logarithm of a product, quotient, root, or power. So what we want to do is we want to expand these. And maybe you remember this, that the log base 3 of 4x over y can be written as the log base 3 of 4x minus the log base 3 of y. If I'm dividing, I can rewrite it as subtraction of 2 logarithms. Do you remember that? Yeah. So then this multiplication here, instead of log base 3 of 4x, I could write as log base 3 of 4 plus log base 3 of x minus log base 3 of y. Good. So as you see this, I have it written in the addition and the subtraction. Notice how y is in the denominator, so that part is negative, whereas 4x, that's in the numerator, so those are positive. No big deal, huh? So how do you want to do that one? Natural log of 8 plus natural log of a cubed. Do you remember what you could do with the exponent for a logarithm? It can actually drop right out front. So this becomes the natural log of 8 plus 3 natural log of a. And those operations become very, very helpful to us. Very helpful to us. We're going to not do letter D, but we are going to do letter C. Letter C says log base 8 of the root of x, or 8 over x plus 1. I'm going to rewrite it as log base 8 of 8 over x plus 1 raised to the 1/2 power. Square root means 1/2 power. What should I do? Put the 1/2 out front. So 1/2 times the log base 8 of 8 over x plus 1. Now I'll break it apart using subtraction. Yep. So 1/2 times the log base 8 of 8 minus what? 1/2 log base 8 of x plus 1. What is the log base 8 of 8? It's 1. Why is the log base 8 of 8 1? Because 8 to the first power is 8. Good. Good job. Look at how smart you are. Now we're going to do the opposite. We are going to take multiple logarithms and rewrite them as 1. So the natural log of 120 minus natural log of 4 could be the natural log of 120 divided by 4. And that gives me the natural log of 30.
You get paid like extra for that?
Yep. All right, we're going to try this one out. I'm going to take the 3 and move it up as an exponent. I'm going to take the 2 and move it up as an exponent. So therefore, I have the log base 7 of x cubed minus log base 7 of 4 plus log base 7 of y squared. What should I do now? Log base 7, what should be in the numerator? X to the third. Y squared. What should be in the denominator? 4. Yeah, if it's adding, it's positive, it will be in the numerator. And if it's negative, it will be in the denominator. Good. We are not going to do letter D, but we will do letter C. I'm going to take care of these parentheses first. Notice that the 3 will go up there and the 5 will go up there. So I have 1/2 times the log of what? What will be in the numerator? 8. X cubed. Y to the 5th. Right? What's in the denominator? Nothing. Nothing's negative. So you can see we have 8, we have x cubed, we have y to the 5th. What should I do is this 1/2? Yep, it'll be a square root. So log of the square root of 8x cubed y to the 5th. That's what that is. All right. Oh, for your birthday. When's your birthday? June 18th. Okay, so your half birthday will be December 18th.
Yeah.
So I'm going to give you a worksheet on logarithms. That'll be your birthday present. Okay.
Okay, that's her, right? For our birthday present. Yeah, for real. That's for our birthday present.
So we're going to solve a couple equations here. Okay. So in this situation, I have 5 to the x is equal to 30. And do I divide both sides by 5?
No.
Do I multiply by a 5th? Do I take the 5th root?
Yeah.
Nope. Okay, so in order to get rid of a base, you use a logarithm. And those are what we call inverse operations. So we're going to operate log base 5 on each side. And what happens is this goes away. What are you left with? X is equal to, do you remember how to evaluate log base 5 of 30 on your calculator? Then take out your calculator. All right, so I've got my calculator. Log base 5 of 30, you're going to do this. You're going to do the log. It's the one with L, O, and G on it. And I'm going to type 30 and my parenthesis. Anybody remember what I do? Divide by log of 5. And I get 2.113. Oh, you said lit. I thought you said wait. Letter B. What are we going to do? Subtract the 5. And I get negative 2 to the x is equal to negative 47. Any thoughts what to do now? No. Divide by your negative 1 and you get 2 to the x is equal to 47. You may not take the log of a negative number. This is extremely important that everybody sees this. This is a big deal right here. We've already talked about it once before. Your brain has to come back to this. What does the exponential function e to the x look like? Passes through what coordinate? So therefore, its domain, okay, its domain is from negative infinity to positive infinity. Everybody agree that's the domain? So you can take e to whatever power. But now you know that that's the graph of e to the x. It turns out that the logarithmic function, which is the inverse, it's going to go through the coordinate 1, 0. It's going to look like this. Notice what's the domain? from 0 to infinity, but not including 0, right? That means you can't take the logarithm of anything over there. Okay, so you see these graphs and their relationship, can't take the log of a negative. Totally illegal. So what I do is I do log base 2 of both sides. And when you do that, you get x is equal to, and I go to my calculator. I type in log of 47, I end my parentheses, and I divide it by the log of 2. And I get 5.555. Or 4, whatever. We're going to skip letter D. Okay. How about letter C? What do we do? Add 8. So I got e to the 2x plus 4 is equal to 42. Now what? Excellent. Michaela says we don't need to use log base whatever. We do natural log because the base of natural log is e. And before we were all confused about e, but hopefully now in calculus you're like, hey, e is awesome because the derivative of e to the x is e to the x. So it is really a beautiful function. We absolutely love it. Take the natural log of both sides there, and we get 2x plus 4 is equal to natural log of 42. How do I do that? Yeah, I grab natural log on my calculator, and I press 42, and I get 3.737. And I'm going to subtract 4. I'm going to divide by dos, which is Spanish for 2, of x equal to negative 0.131. Not too bad. Not too bad. We move on to letter G, and we will also do letter I. Can somebody tell me, how do I get rid of log base 3? I create a base of 3. Remember that? So if I create a base of 3, what's going to happen? Those go away, I get x is equal to, which is 9. Let's try letter I. What do I do to both sides? Minus 7. I get 2 times the natural log of x is equal to 1. Divide by 2. The natural log of x is equal to 1/2. How do I get rid of natural log? What's the base of natural log? I create a base of e, and I get x is equal to, what does it mean to take e to the 1/2 power? So you could write as the root of e, or you could find the decimal. She likes root of e. Prettier. You've used the words pretty for something mathematical. I like it. Makes me happy. Flip it over. Ah. Ah. What? I don't know. I don't really watch my students. I just teach. So whatever they do, they do. If you have an exponential function, we just talked about what point does it go through? 0, 1. So all you got to do is just graph the function like that. It doesn't matter if it's e to the x, 4 to the x, 8 to the x, 9 to the x. It looks like that. Do you remember what happens if it's a 1/4? It's going to flip. If it's less than 1, then it's going to go like that. So what's 2 to the x going to look like? Is it going to look like the first one or the second one? First one. What's going to happen if we have a negative 8 to the x? It's going to create that vertical flip. So instead of going through 0, 1, it's going to go through 0, negative 1. Looks like that. What happens if you have 3 to the x minus 4? Shift it all down 4 units. And you guys have learned a lot in the past 2 years. So instead of going through the point 0, 1, it's going to go through the point 0, negative 3. So the asymptote, notice how we always draw it along the x-axis, that's the asymptote, but the asymptote shifted down 4 units So we get that graph. We're good with that? Okay, we'll ask a couple problems. Sorry, Hattie, for another chicken dance in the video. I know. All right, let's see what we remember. We're almost done. What is the logarithmic graph going to look like? Yeah, we just talked about it, right? It's going to be the inverse, so it's going to go like that. So it doesn't matter if it's log base e, log base 2, log base 10, natural log, it's going to look like that. What's going to happen if we do log base 5 of x minus 2? This is down 2. This would be left 3. See the difference? If it's on the outside, it's down 2. If it's on the inside, in that case, left 3. So we're going to move it down 2. So that means that instead of going through the point 1, 0, it's going to go through the point 1, negative 2. Yep. So this one, we see x plus 3. What's that going to do? Shift it to the left 3 units. 1, 2, 3. So you can see in this situation that the asymptote, instead of being along the y-axis, the asymptote is shifted back 3 units. What coordinate is it going to go through? And the last one we'll do is letter J. What's going to happen there? It's going to flip, yep. So it's going to start up, and then it's going to finish down like that. Okay. Yeah, if you had log base 4 of a negative x, then it would flip that way. We won't do that. Okay, before we end today, you've learned some very important numbers in math. And as we extend calculus even further, and those of you who take calculus 2, maybe your professor will take you through this. I've always wanted to be able to end our year this way, but I feel like I would enjoy it more than you guys would. But there was a very famous mathematician by the name of Leonard Euler. I've mentioned him before. Kind of 4 greatest minds we've ever seen face the earth. We would say Isaac Newton. We would say Leonard Gauss. Frederick Gauss. And then Archimedes, but another one would be a man by the name of Leonard Euler, and he came up with just a crazy equation, and this is the equation. You know E, right? And you know I, right? And you know 1, and you know 0, and you know pi. So obviously pi is very highly tied to geometry, correct? And we've also seen it play its role in trigonometry as well. 0 is that great number that's used in so many situations of mathematics, is it not? And so is 1. I is like that fundamental number that's used within an imaginary situation. And E, we've learned in calculus how important E is, right? It just so happens that all of these numbers can be expressed as one beautiful equation. And it just so happens if you take E and you raise it to the I pi power and you add 1, you get exactly 0. And you should not be able to look at that and say, oh, I know exactly what that means. It took me many years before I finally understood what that means. But as we move through calculus, that equation is shown to be true. It's one of the most famous equations out there. Beautiful. We don't know all the things that will come of it as of yet, but we're wondering. We make breakthroughs every day. So, you have time to work. Maddie has the first question, and it's on the motion problems. So I'll stop my video. We'll get